might sequence what I call the dynamic duo. Now, many may not recall this old series of Batman and his sidekick Robin. So I call these two cell types we're going to talk about mast cells and microglia as the dynamic duo of inflammation. Mast cells, if you've not seen this before, have a very characteristic property, which is these granules in the cytoplasm, which are filled with various agents involved in inflammation. This one is stained for histamine. The other cell type, which I think is very important in inflammation, are the microglia. This is staining of microglia in the brain. It's a snapshot in time. In reality, the cells are not static, they're very dynamic. They have these processes which retract, expand. What they do is they survey their environment. So it's sort of a biosensor, or what you might think of as a smoke detector in the brain, looking for adverse events, injury, and how they might respond. And they do, of course, have a beneficial effect. When there's injury, they phagocytose debris. But this effect can produce an inflammatory response. Mast cells go back quite a while, 1870, described by Paul Ehrlich. They derive from the innate immune system. Usually we think of mast cells as being linked with an antigenic response. They respond to antigen. If you are sensitive to plant pollen binds to Ig receptors on mast cells, provokes release of histamine, and this is what causes an asthmatic reaction when you have bronchoconstriction. They also, like many cell types, there's a flip side to the coin. They also are beneficial. They participate in wound healing and tissue remodeling. One particular feature of mast cells is you find them at sites in the body which are close to the environment. You find them in epidermis and dermis. When you have a mosquito bite, the redness and swelling in the skin is due to release of histamine from mast cells. They're found in bronchial airways, so when you have, as I say, response to an allergen, the mast cells release histamine, you have bronchoconstriction and an asthmatic attack. They're close to blood vessels and also close to nerves, to nerve endings. I think of mast cells as sort of a jack of all trades immune cell. They respond to antigen, to neuropeptides, cytokines, chemokines, to extremes of temperature and pressure. You may find sometimes if you're out jogging in the cold and you inhale cold air, this cold air can provoke mast cell degranulation and asthmatic reaction to cold air. They express agents that allow interaction with T cells. So they will bind T cell, and actually what has been described as an immunological synapse, but that's another story. They have these granules which are packaged with agents like histamine, serotonin, heparin, the only cell in our body which makes heparin, proteases, which can participate in tissue degradation. They have preformed cytokines. They have T and B cell ligands. They have, besides these also, they can make agents de novo. So they can synthesize prostaglandins, leukotrienes, which act as chemoattractants, cytokines. So TNF can be both preformed and also made de novo. Growth factors like neurogrowth factor, which participates in pain, they don't make mitogens, they don't make FGF, MMS growth factor, however. The chemokines, free radicals, neuropeptides like substance P, so quite more than 50 substances which mast cells make. they don't all make the same thing. They're very heterogeneous, depends on the species, and depends also on the cells in which they are found. So mast cells are heterogeneous depending upon where they are expressed. This is a nice picture of a mast cell, tissue mast cell, undergoing degranulation. These granule cells are labeled for histamine. So as you can see, the footprint is actually quite large. They'll travel about 50 micrometers from the cell. They are also perivascular, they're close to nerves. This one is close to a small blood vessel and also to a nerve. You can see the neuron there. This mast cell is in the brain parenchyma. I'm not sure what the label is, but you can see they do, when they degranulate, they can travel quite some distance. So if you superimpose this footprint on this image, when it degranulates, those granules cover quite a bit of territory. Now, when you think, people look at a mast cell and they see degranulation and think the thing, it blows up, and that's it. It's not a one-trick pony. They, apart from this, and also making agents de novo, they will also, they're stable actually, they will recycle, and they can go through multiple cycles of degranulation, which makes them rather dangerous in that respect. Now, both mast cells and microglia participate in inflammation, particularly low-grade inflammation, which is persistent inflammation. It's really not like being struck by lightning, but something which doesn't go away. This low-grade inflammation, which releases, among other things, inflammatory cytokines, has a variety of influences. It's not sensory receptors in the periphery, nociception, pain, for example, which also has an effect on pain transmission centrally, which I'll get into briefly. They can influence both the blood-brain barrier and blood-spinal cord barrier, and they can also activate microglia. Now, apart from their participation in inflammation, mast cells and microglia don't act alone. There's good evidence that they all can influence each other, communicate with each other. Just a couple of examples of this. What is called proteinase activated receptor 2, PAR2, is expressed on both microglia and mast cells. Now, mast cells, when activated, release proteases, which will cleave and activate PAR2 on microglia. This activates a receptor, P2X for purinergic, which leads to release of brain-derived neurotrophic factor. BDNF, in this case, actually participates in pain transmission. So it's pro-pain. Now, microglia, when activated, release IL-6, which can upregulate PR2 expression of mast cells. So these two, which are also close in sites of inflammation, work together and create a cycle. One example. Another one, they also can create this cycle of communication through chemokines, also through complement. C5a receptor and complement C5a are both expressed on microglia. They're upregulated in settings of inflammation. Mast cells express the receptor but not the chemokine. However, the chemokine is a strong chemoattractant for mast cells. So again, microglia producing C5a will attract mast and microglia to the site of inflammation where the microglia are also. So again, these cells work together. What you have essentially is a cycle between mast cell and microglia in which the agents which they release feed on each other and create a vicious cycle. Now, if this were not bad enough, you have to think about imposing on this effective aging. Now, in aging, when we're faced with what is called immunosenescence, so in effect, immune cells, like mast cells and microglia, become more sensitive to an insult. They become, in effect, hyperreactive. So this amplifies the entire response. Also, in some settings, with aging, they will also proliferate. So this increased sensitivity plus proliferation amplifies this cycle. And they become sensitive to even very mild stimuli, which ordinarily would not provoke a reaction. So even a mild stimulus, which is continuous, can create a setting of low-grade inflammation which fails to resolve. And this can also act both spinally and supraspinally to create a persistent state of pain, even low-grade pain. Now, you can do, this just shows very schematically that when you have this hyperreactivity, normally mast cells or microglia will release a cytokine, goes up and comes down, but the whole process becomes very protracted in aging. So these cells, in essence, become primed for some reason, not fully understood, where with this priming, they respond to very mild stimuli. Now you can show priming, very simple example, in cell culture. If you take microglia, the cortex or spinal cord, and expose them to agonists of TLRs, TLR is called toll-like receptor. These are receptors, they're category molecules called danger-associated molecular patterns. So these TLRs are family of receptors which respond to families of pathogens. For example, bacterial endotoxins or viral agents, viral double-stranded DNA or RNA will activate some TLRs. Injury, release or breakdown of nucleic acids and proteins will act as ligands for TLRs. If we look at models of neuropathic pain in rats, look at microglia, they have activated TLR2 and TLR4 on their microglia. Now, microglia priming, if you take and expose them, we've used LPS, which is produced by gram-negative bacteria in the cell wall. So this LPS is a ligand for TLR4, and zymosan is produced from extract of yeast, TLR2 agonist. So expose the cells for a few hours to these agonists. They release some interleukin-1 beta, the pro-inflammatory cytokine, which is actually sort of the master pro-inflammatory cytokine. Now, if you take, after this treatment, add ATP. Why ATP? ATP is actually considered a danger signal. When you have tissue injury, ATP is released. It activates cholinergic receptors, which participate in inflammation. So if you prime them with LPS or zymosan, then it adds ATP, there's a very large increase of release of IL-1 beta, which would not occur with ATP alone. So in essence, the cells are primed and ready for a second hit, the two-hit hypothesis of inflammation. Just an example of agent rat brain in spinal cord. Look at microglia, you find them in an activated state. Their numbers much more so than this is a 2-month-old rat as opposed to 18-month-old. So this senescence occurs where these cells become more reactive. Another example, moving partial liver in the animal, the rat, and then imposing an inflammatory stimulus with LPS. You can grade the stimulus. Give a little bit of LPS, nothing happens. But if you give a small amount of LPS to these animals, what you get is response to mechanical stress. Take the foot, the paw of the animal, and apply a pressure. Normally, you apply pressure to a certain point, they will withdraw. But in this case, they become very sensitive to a very small amount of pressure called allodynia. It's mechanical stress. So when you apply this stress and apply a second stress, they show increased responsiveness and also increased activity of microglia in the tissue. So the upstart to all this is that aging will sensitize the immune system to reactivity. LPS, if you look at cognition, giving LPS peripherally will lead to inflammation centrally. And normal animals that wouldn't respond to a low dose of LPS will show a cognitive deficit when they age. Now, if you look at elderly people that have a cognitive deficit and experience an inflammatory episode, influenza or delirium, if after an inflammatory episode, oftentimes their cognitive deficit will worsen, so that inflammatory episode can worsen. Now, let's look at pain transmission. Pain can start in the periphery, but it's expressed centrally. Now, if you have a chemical stimulus or injury in the periphery, mast cells become activated. They release agents which act on nociceptors, somatosensory neurons, first-order neurons, and this influences their excitability. This transmits a signal to the spinal cord, which also has mast cells in the dura. These spinal cord neurons, second motor neurons, become activated, transmit a signal to the brainstem to the thalamus. Now the thalamus is very rich in mast cells. Inflammatory mast cells become activated. These are stained for histamine and serotonin. Become activated, release agents which act on neurons in the cortex, and in the end, to make a long story short, we perceive as pain. Now, interestingly, if you take and injure a peripheral nerve, they can constrict or transect the sciatic nerve, and look several hours later in the thalamus, you'll find mast cell degranulation. So the signal will transmit from the periphery centrally. Now, talking about inflammation and cognition in the elderly, I came across a fascinating paper that came out in Nature a few months ago, looking at the effect of dietary emulsifiers and metabolic syndrome. Metabolic syndrome is found oftentimes in the elderly, and it's a good example of low-grade but persistent inflammation characterized by obesity, failure to control blood glucose, and also fat accumulation. Now, why emulsifiers? They looked at two very common ones, one called polysorbate 80, the other called carboxymethylcellulose. They were used very often in processed foods. And these emulsifiers given to rats provoke various aspects that one would find in metabolic syndrome. Now, if you go to a supermarket in Italy and look at the aisle where they sell pasta, you'll find the aisle may stretch from this wall to this wall with pasta. If you go to a supermarket in the US and look at the aisle that sells processed foods, that aisle probably stretches from this room to the back of the room. Processed foods contain a lot of things like emulsifiers. And processed foods are very popular with the elderly, people on fixed income or low income who tend to eat a lot of processed foods, also because it's convenient. If you spend time in the supermarket in the US looking at people and what they shop for, you'll find very often people of a certain age filling the baskets with these processed foods. And just looking at these, you'll find very often they tend to be, I would say, overweight if not clinically obese. And eating these foods which have these agents can also contribute to metabolic syndrome, a low-grade non-resolving inflammation in the elderly. Aging has various consequences which can also influence both how we respond to what we eat and also the drugs that we take. Without going into all the gory details, which contribute to metabolic syndrome, but also the elderly often are on polytherapies, take multiple drugs for a variety of problems. And apart from the problems which they have, aging increases how we metabolize drugs, which makes them also sensitive to more so to side effects of drugs. They're often being treated for pain. Now, there are a variety of drugs used commonly for pain, ranging from the non-steroidal anti-inflammatories all the way to antidepressants, antiepileptics, and opioids in cases of chronic neuropathic pain. They all have their use. They have utility up to a certain point. Opioids, of course, have for neuropathic pain. Many people don't respond or respond poorly. There are issues with things like, of course, tolerance and dependence, and also how they respond to these can also depend. The pharmacokinetics and dynamics of how one responds to a drug will change with aging. So, with this in mind, I think I'm just going to pass a couple of slides. So the take-home message is that these players in inflammation, mast cells, and microglia undergo change in reactivity with age. If we look in the peripheral nerve, in the endomural compartment, where there are mast cell numbers increase with age and also become more reactive. This can also affect how the primary somatic sensory neurons respond. We call the diagram pain transmission from the periphery to the brain. And these hyperreactive mast cells release enzymes which can also physically alter or damage the fibers involved in pain transmission. And of course, microglia, when they age as a part of senescence, not only become overactivated but also become resistant to our attempts to regulate them. And again, aging is associated with changes, metabolic changes in how one responds to drugs, which can lead to worsening of side effects and also response to dosing. Now, another important point is that when we think of inflammation and pain, which are very well connected, is that there is the link between the immune and nervous systems, but also one needs to think about how components of the immune system interact with each other and how this interaction affects the nervous system. So it's really sort of like a triangle between these different immune cell types and neurons. And oftentimes drugs that are used to treat pain target the neuronal aspects of pain. They target neurons. But I think why many of them are not always effective, like opioids, is that they target the neuron, but they don't take into account the contribution to the pain and inflammation of the non-neurons. So I guess the final message is that developing more effective and safe therapeutics to treat these non-resolving inflammatory conditions are to target all the cells involved in the cascade and not just so a multimodal approach, as someone would say. So with that, I think I'll stop. And if anyone has any burning questions or non-burning questions.
Okay, thank you very much, Stephen, for this excellent survey.